The floor is yours.
Good morning, everybody. I am Francesco Collini from the University of Padua, and today I will talk about notch fatigue for metallic materials under local multi-axial loading conditions. Here you can see the agenda of my presentation. I will start with a short introduction to motivate the engineering interest behind studying local multi-axial fatigue for notched components made of additively manufactured materials. Then a deep dive into the theoretical background of the notch effects on fatigue behaviors of metallic materials, focusing especially on the effects of the notch size and its acuity, before introducing the average strain energy density models and some manipulations to determine the fatigue limit with this model of notched components under multi-axial loading conditions. And lastly, the validation of the proposed equations against the experimental data coming from the literature and the conclusions. So starting from the introduction, consider a generic lattice structure subjected to a set of remote loads as schematized in this slide. If we look closely at the lattice structure on the scale of individual unit cells, we can see that due to the porous nature of lattice structures, they are inherently notched, resulting in severe stress concentrations at the nodes, which are characterized by the presence of multi-axial stress fields ahead of such nodes. And this is very interesting because it is independently of the remote loading conditions. So moving on to the theoretical background, consider a generic notched specimen with subjected to a remote stress field of the amplitude sigma g and of size 2a and notch deep radius rho. If we plot the opening stress field along the notch bisector in a B-logarithmic scale under the hypothesis of linear elasticity, we obtain the schematic stress field shown in the figure, which is characterized by three different regions. The first, dominated by the KTG, which is the theoretical stress concentration factor. Then, if we move along the notch bisector, we encounter the singularity, the notch singularity region, which is dominated by the stress intensity factor K prime with a singularity exponent 0.5, before eventually asymptotically reaching the sigma g, which is the remote stress field. Changes of the stress of the notch tip radius, the stress concentration factor will move up and down, while the changes of the crack size of the notch size, the singularity region will move to the left or to the right. So we can expect different fatigue strength or different combination of the notch size and its notch tip radius. In general, it is common knowledge that the larger the notch and the more acute the notch, the lower the fatigue limit. However, the relationship is far from that straightforward and can be really comprehensively analyzed in a Meneghetti diagram, where on the x-axis, we have the effective crack size or effective notch size of the notch, and on the y-axis, we have the fatigue limit. The curves you see plotted in this diagram are obtained by changing the size of the notch in a geometrical similarity. So by moving to the right, the constant, the ratio between the notch tip radius and the notch size is kept constant. We can see that inside a single design curve, there are different regions can be identified, which are related to different fatigue behavior of notched components, each of which is due to different physical phenomena. And it is very interesting that a single design curve can summarize all these different fatigue phenomena. Similar results can be obtained for V notches, where the only differences are related to the stress singularity exponent, which is no longer 0.5, but changes between 0 and 0.5. And in the sharp notch region of the Meneghetti diagram, where for different notch opening angles, we obtain different design curves. However, for a fixed opening angle, there is only one single design curve that can be adopted across the whole range of notch sizes. And I believe that this is the beauty of this diagram, because by being able to summarize all these different behaviors, it suggests that to the engineer that there exists a single material model that can be used across all the Meneghetti diagram. A possibility for that is the average strain energy density model, which is based on Neuburg's engineering idea, according to which the fatigue strength is sensitive to the mean stress in a small but finite characteristic volume surrounding the stress razor. With reference to the figure sketched on the left, according to the average strain energy density model, the structural volume is defined as a circular sector of radius RC, while the mean stress can be quantified by the average strain energy density inside such structural volume. I want to show you in the next two slides how with this very simple model, it is possible to describe all the Azzarri Meneghetti, focusing, starting by analyzing the full notch sensitivity region, which is for very large and blunt notches. If we analyze the stress field ahead of the notch tip for such a notch, we can see that inside the structural volume I chose schematically, the stress field is dominated by the stress intensity factor, by the stress concentration factor KTG. And so we can expect this notch to be, this combination of notch and structural volume to behave to fall in the full notch sensitivity region, since it is dominated by the KTG. If we now consider a smaller notch obtained in geometrical similarity, now the stress singularity field shifts to the left, and we see that the stress field inside the notch is dominated by the stress intensity factor. And so we can expect that this notch will fall in the long crack or sharp notch region of the Azzarri Meneghetti diagram. For a more detailed analysis, I suggest you to read this article from 2005 published by Professor Lazzarin and Professor Berto, where they analyzed with the with the strain energy density model, all the Azzarri Meneghetti diagram. I want now to focus your attention on the prediction of the fatigue limit of sharply notched materials, where the fillet radius is so small we can neglect it, under local multi-axial loading condition as schematized in the figure. According to the equation provided in the two referenced articles, it is possible to link the range of the average strain energy density in the structural volume to the notch stress intensity factors that I showed you before for mode 1, 2, and 3, according to this equation. Then, under the hypothesis of linear elasticity, it is possible to estimate the notch stress intensity factors as a function of the notch size, that you can see here A, and the remote load applied, delta sigma G. By plugging the second equation into the first equation, we can, and particularizing the obtained equation to the threshold conditions, we can obtain a relationship between the range of variation of the average strain energy density in threshold conditions and the fatigue limit of the material expressed in terms of delta sigma G and the notch size. By proper manipulations of algebraic manipulation of the obtained equations, we reach this very simplified formula, where at the numerator, we can see a sort of equivalent threshold notch stress intensity factor, and the denominator, an equivalent crack size. And I want to highlight this last equation is very familiar, and it is formally identical to the prediction of the linear elastic fracture mechanics for a centered crack in an infinite plate. And so, as schematized in the left-hand side of the slide, we obtain a sort of equivalent centered crack that is representative of any notch of any size subjected to any local stress field ahead of the notch tip. So moving on to the validation of the proposed equations, I took data from an article published by Professor Azzori and co-workers in 2006 on the International Fatigue Journal, where the authors analyzed two different specimen geometries, in particular a cylindrical V-notched specimen and a cylindrical shaft. All the specimens had a V-notch opening angle of 90 degrees, and the material chosen was a normalized low carbon steel C40. The specimens were machined and polished after the machining process. The structural radius was equal to 0.4 millimeters, and the delta WT in threshold conditions was 0.33 megapascals. By comparing the numerical prediction that you can see as a black line in an Azzarri Meneghetti model against the experimental data, we can see, starting from the test obtained for only tension loading, so only tension loading for the V-notched specimens, a very good agreement between experimental and numerical data. Moving on, for the torsion loading conditions, again, we see that the prediction is coherent, also there are no data falling below the prediction line. And lastly, also for remote multi-axial loading conditions, again, there are no data falling below design, and so we can say that this model is able to predict the fatigue limit for a wide variety of local stress fields. Here you can see in more detail that the comparison for all the different multi-axial loading conditions. And so in conclusion, using the average strain energy density model, it was possible to obtain a single design curve for any, to predict the fatigue limit of any sharply notched components subjected to any remote loading conditions. oh, sorry. And by comparing the experimental results with the numerical predictions, it was shown that we obtained very good, very promising results for different geometries of sharp Fibonacci specimens under different loading conditions, including multi-axial tension plus torsion, and both in phase and out of phase loading conditions. With this, I conclude my presentation. Thank you for your attention. And if you have any questions, please feel free to ask.
Thank you. From the audience, is there any question? We have time for one question. Then it's me. So you mentioned on the title, of course, and also in your presentation, that the method can be used for mode 1, 2, 3, or any combination.
Yes.
Usually in our field, we are used to going for cylindrical specimen because it gives very clean mode 3. But how can you incorporate, for example, coupled mode if someone is performing mode 2, pure mode 2? Okay. Or pure mode 3 on a plate? How can we implement that or consider that using this procedure that you presented for us?
So you are asking how can I include mode 2 loading only, for example, in the proposed equations?
Yeah, because on the plates, even if we apply mode 2 or mode 3, we will not only get that mode. There would be a couple mode with it.
Yes. So the proposed equation, as shown in this slide, was obtained for sharply notched specimens, and it would just be sufficient to estimate the notch stress intensity factor obtained by applying the remote loads. And so by computing the contribution of the mode 1, mode 2, and mode 3 only, we can obtain a different value of this AU effective.
Okay, okay.
So it could be very general then. There are the approximations related to the validity of the SED and the strain energy density model. However, at least from an analytical perspective, it's extremely robust.
Yeah. So even if for the cases that we expect that we may have coupling, we can consider all terms.
Yes,
yeah.
Absolutely,
okay.
Yes.
Thank you so much. Thank you.